Okay, so in this chapter so far, we reviewed two functions. We reviewed what a linear function is, what an exponential function is, and what the new function, a quadratic function is. Right? So now, remember, a linear function, right, has a common difference. Okay? It has an explicit rule that is in the form of f of x equals slope times x minus x1 plus y1. All right, now you had a recursive rule, right, that started off with f of a number equals a number, and then we said f of x equals your previous term plus that common difference. Okay, now when we graph, right, a linear function, it's much easier to probably graph from an explicit or a table, right? But if we were to plot all the points that make the explicit rule true and we graphed it, it would be the graph of a straight line. Okay, now an exponential function had a common ratio. Okay, its explicit rule, right, would end up being f of x equals a times b to the x, where a is your initial amount, b is your common ratio. Then the recursive rule, right, would be f of a number equals a number. And then what are we doing to the previous term each time? We're multiplying the previous term by the common ratio. So it's the common ratio times the previous term. Now when you graph this, right, we have exponential growth. If we have growth, that means b is greater than 1, right? And your function starts out small and grows quickly. We have decay, right? And decay is when b is greater than 0 but less than 1. And that starts high and decreases real quickly. Okay? Now a quadratic function, right? We know a quadratic function has a common second difference, right? The explicit rule for this, right, is f of x equals ax squared plus bx plus c. What makes this a quadratic is this x squared term. Okay, that's the most important part to know. Now, the recursive, although you're not responsible for this, right, I'm just going to go ahead and explain it real quick. F of a number equals a number, and then f of x equals the previous term plus, right, some number times x plus some constant. What this shows, right, what that shows is it grows with a linear rate of change. Okay? So when we talk about linear, exponential, quadratic, what is the difference between the three? When we talk at the rate of growth, right? The rate of growth of a linear function is constant, right? And that's because it goes up the same amount each time. When we talk about an exponential function, the rate of growth is exponential. And the reason is it grows, when anything grows real quick, right, it means it grows exponentially. Now, a quadratic function, all right, number one, when we go to graph this, the graph is a parabola. So when you graph it in the coordinate plane, right, you end up getting a parabola that looks like a U. And these parabolas have a vertex, right? And they're what we call symmetrical, meaning you can cut it in half and this side would fold on top of that. The rate of growth for this, the rate of growth for a quadratic function is it grows in a linear fashion, right? It has a linear rate of change in it. If you see that, it all goes that you're adding a linear growth, right, to the previous term each time. Okay, so the next task goes ahead and talks about a bunch of different scenarios, graphs, tables, situations, right? And we have to identify if it's a function or not, determine if it's linear, exponential, quadratic, or neither, describe the type of growth, and then create one or more representations for the relation. Now, what I would like to see you guys do is attempt the problems on your own, right? And then come back and check your answers. So do the problem, unpause it, go through the video. So number 1, a plumber charges a base fee of $55 for a service call plus $35 per hour for each hour worked during the service call. The relationship between the total price of the service call and the number of hours worked, right? So right away when we look at this, if we start with 55, right? So right away when we look at it, 0 hours worked, right, would be $55 just for showing up. 1 hour work now would be the 55 plus 35, which would give you $90. After 2 hours, it'd be 55 plus 35 plus 35, which gives you $125. So if you make a table of this situation, you'll see you have a common difference of 35. If you have a common difference of 35, right, that means your function, it is a function. This function is going to be linear, and it grows, right, at a constant rate of change. Okay, now the table can act as one representation, right? So I can go 3, that'd be 160, and so on. But if we want to write the explicit rule here, okay, if I take right away just the first ordered pair, which is the y-intercept, I can say f of x equals, right, my slope is 35, times x minus x1, which is 0, plus my initial charge of $55. You could also write this as 35x plus 55. Either one of these would be okay. The recursive rule, f of 0 equals 55, f of x equals my previous term plus 35. Okay? Now, by looking at the graph of number 2, okay, right away we know this is a parabola. Okay? So this is a parabola, which means right away this passes the vertical line test. So this is a function, right? This function is a quadratic function, which means the rate of growth is going to be a linear rate of change, right? And I could do a couple of things here for a representation. I'm going to give you 2. 1, for all quadratics, if you can't think of the quadratic function, right, create a table. And when I create my table for a quadratic function, I'm going to put the vertex in the middle, 0, 5. Then I'll go -1, 4, -2, 1, and I'm going to go 1, 4, 2, 1. this right here would be the table for the quadratic function with the vertex in the middle. Now, the explicit rule, if you wanted to write it, right, f of x equals, if you look, anytime it opens down like this, f of x equals negative x squared, right? So it's going to be negative ax squared plus bx plus c. And in this case, it would be negative x squared plus 5. If you don't understand the explicit, don't worry. We're going to talk about those more in Unit 2. Number 3, right away we know it's a function because it passes the vertical line test, right? Now when I look at it, it may be difficult to tell which one it is. Is it going to be a parabola or is it going to be exponential? So what I would do is go right away to letter D, the representation, and I'm going to create a table. And I'm going to say -3, 8, -2, 4, then what is that? -1, 2, and 0, 1. What am I doing each time here? Here I'm dividing by 2 each time, or basically multiplying by 1/2. Okay? Which means this is going to, since it has a common ratio, this is going to be exponential. It's going to grow at an exponential rate. To write the explicit rule, right, for another representation, the explicit rule, I'm going to gather the initial amount, which is 0, 1, right? I know my common ratio, right, is 1/2 because that's what I'm multiplying by each time. So f of x equals 1 times 1/2 to the x power. Now the recursive rule, right? The recursive rule is going to be f of 0 equals 1. Then f of x equals 1/2 times the previous term. We are done. Number 4, right away when I look at this, if I were to multiply this out, this would give me x squared, right? Just by doing x minus 2 squared, right? That's x minus 2 times x minus 2, right? So right away when I multiply this, I get x squared. As soon as I get this, 1, I know it's a function, but what type of function is it going to be? This is going to be a quadratic function. All right. Now, again, the rate of growth is going to be linear rate of growth. And if we had to do a representation for this one, what I would do is just create a table. Okay. So you're already given the function. So the table, right, I'll just plug ordered pairs in. So if I start with, say, 0. If I plug 0 in, 0 minus 2 is 2. Negative 2. Negative 2 squared is 4. So it's going to give you 4/3 times 4. 1/3 times 4, which is 4/3 plus 4 would be 0, 4, and like 4/3, which we don't want to do that. So it'd be 5 and 1/3. Okay, this gets chaotic. What I would tell you to do, just go to your calculator, right? Go to y equals and plug that function in. So I'm going to go 1/3. So alpha y equals 1 over 3. Then I'm going to go open parentheses x minus 2 all squared plus 4. Now when you hit the graph, right? Let me turn my stat plots off. When I go to hit the graph, notice what I get here. I get that parabola, so I know it's quadratic. But to create this table, what I would do is go second graph to get the table. Then all I'm going to do is pull all the nice numbers off here. So, let me pull that back up. So I'm going to write down, say negative 1379. Let me scroll down. Another one would be negative 731. Then another one is going to be negative 17. And then if I look, when it's 0, is it nice? Not really. But at 2, 4. So this table can be used as a representation, okay? And you can get that table from the graph. Now, what I like to do is I like to find, right, the vertex. And if I go zoom 6 to get in the standard window, my vertex looks at around 2, 4, right? So if my vertex is at 2, 4, watch where this symmetry comes in. If I go to the table, 2, 4, now look at when I get to 5. What am I at? 5, 7. So right away, if I look, see the symmetry here? So right away, when I go up, again, the next nice y value is going to be 31. So at 11, 31. And again, see the symmetry? All right. So keep that in mind. Number 5, that is not a function. Okay. Number 6, you have to see that this follows m times x minus x1 plus y1, which tells me A, this is a function, right? B, it's in the form of a linear function. C, right away when I look at it, that means it has a constant rate of change. It's going up the same amount each time. And D, right, if I had to do a representation, right, 1, I can create a table, right? Now, when I create a table, I know my slope is 1/3. So if I want to, I can go here again, and I can just type in, alpha y equals 1, arrow down 3. Times x minus 2, right, plus 4. And when I look at it, this would be my linear function, right? So I could graph that. But if I go to the table, I can get some nice points off it, right? So if I look, I can go negative 1, 3. Another nice ordered pair would be 2, 4. Then even if I wanted to, I could go 5, 5. So that table would be a representation. If I were to graph it, I can graph to these points. So negative 1, 3, 2, 4. And right away when I graph that, that would be the graph. If I wanted the recursive rule, I would use one of the ordered pairs. Then I know my common difference is going to be 1/3, right? My common difference is 1/3. So f of negative 1 equals 3. Then f of x equals f of x minus 1 plus 1/3. Okay. So for this one, you'll see all of my x values are going up the same amount each time. But what's going on here is if I go ahead and I subtract the first ones, right? 50 minus 12.5. So right away, when you look at your first difference here, right, you get these values. So you know it's not linear, and you know it's not exponential because there's no common ratio. But when I take the second difference, right, this gives me 25, this gives me 25, this gives me 25. And if it has a common second difference, 1, it's a function. 2, we know that function is going to be quadratic. All right. We know it's a linear rate of change. Okay. And then D, if you had to do a representation here, this could be a real hard explicit rule to come up with. So just go ahead and take a graph and plot all of these points. When you plot all of these points, you should see that it ends up being like something like this. Now, we should duplicate it on the other side to see that it's going to be a parabola, right? And it's not exponential. All right, anytime we get problems like this, what should we always start with to determine if it's a function or not? Should always start with a table. So we have 1, 1, 2, 3, 3, 6, 4, 10. Now, when I look at this right away, right, there's no common ratio. So what I can do here is look, that's up 2, up 3, up 4. Right away, if I look for the common difference, up 1, up 1. So this has a common second difference. So A, it is a function. B, right, this function will be quadratic. C, it has a linear rate of growth, or rate of change. And D, if I just took this, the table can be a representation, or I could go ahead and plot those points and get a graph. Now, the rate at which caffeine is eliminated from the bloodstream of an adult is about 15% per hour, right? The relationship between the amount of caffeine in the bloodstream and the number of hours from the time the adult drinks the caffeinated beverage, if the initial amount of caffeine in the bloodstream is 500 milligrams. Now, anytime you increase or decrease by a certain percent, right away you know that is a function, and you know because you're going down a certain percentage that this is going to be exponential. Okay? If it's exponential, it grows, and in this case, this would be exponential decay, right? Now, if I make this table, it would be 0, 500. Now, after 1 hour, right, you have to remember, I'm basically, if I'm going down 15%, that means I'm at 85% each time. So I could basically do 500 times 0.15. Remember, anytime we use percentages, we change them to decimals. So 500 times 0.15, all right, that's 75. So now, how much caffeine is left? 500 minus 75, which gives me 425. Now, an easier way to do that is if it goes down 15%, how much is left? 85%, right? So if I do 100 minus 15%, that gives me 85. So now if I take 500 times 0.85, right? 500 times 0.85, what do you get? 425. This is a better way to look at it, right? So now if I go to 2, now I'm going to do 425 times 0.85. That's going to give me 361.25. So now right away, this table would be a representation. You know it's exponential decay, and you can go ahead and graph it, but you know the numbers will be tough. But let's go ahead and write our explicit rule. Right? We know we start with an initial amount of 500 times, what is our rate of growth right now? Since we're going down 15%, that means we have 85% left each time. So it's 0.85 to the x. And if you look here, right, y equals 500 times 0.85 to the x power. And if I go ahead and go to the table, I will see 0, 500, 1, 425, 2, 361.25. And if I graph it, it's really not going to show because it's outside the window. But if I go a y max of 500 and graph it, you will see that. Okay. Number 10, right away when I write these ordered pairs. Okay, I look, this is 0, 1. What is that, negative 1, 2? What is that, negative 2, 3? And so on. I have to know that A, this is a function. B, this function is linear. C, has a constant rate of change. And D, first off, if I go and write the explicit rule, right? The explicit would just be f of x equals my slope or rate of change is it's going up 1 each time. So it's 1 times x minus 0 plus 1. Now I could also write that as 1x plus 1. Okay? 11. If I were to FOIL these out, it would give me 4x times x is 4x squared. 4x times negative 6 is minus 24x plus 3x minus 18. So that ends up being 4x squared minus 21x minus 18. Right away, I know that's a function. And what type of function is it going to be? If I have this x squared here, that function is going to be quadratic. C, I know it's a linear rate of growth. And what I would do is just create a table. All right. And then take that table and graph it. Now, when you graph this one in a calculator, you'll see that it doesn't show up in the window, right? So anytime you want to see more, you should see the vertex looks like it's going to be down here somewhere. So let's go ahead, and when we want to change that, we want to go down. So we're going to change the y min, and let's just say negative 30, just to try and get it in there, right? Oh, still didn't get it in there, right? So let's just change the y min again. Let's go negative 75. Now we can see the vertex. All right, let's look at the next one. All right. Mary Contrary wants to build a rectangular flower garden by a walkway 4 meters wide. So here's a rectangular flower garden. It will be 6 meters longer than it is wide. So if this here is our garden, right? And then I'm going around it, right? And I know that the width of this is going to be 4. Okay? So remember, it's going to be surrounded by a walkway 4 meters wide. So that's 4 meters, that's 4 meters, that's 4 meters, and this is 4 meters, right? What is the relationship between the width of the garden and perimeter of the walkway? So let's just look at the garden real quick. So now the garden, we know it's, excuse me, it says the garden will be 6 meters longer than it is wide. So if this is my length and this is my width, I'm basically going to say the length is going to be the width plus 6, right? So now when I go to look at the perimeter of the garden, the perimeter of the garden is going to be W plus W. Remember, perimeter is distance around, plus W plus 6 plus W plus 6. So the perimeter of the garden will be 4W plus 12. Now, this is going to be linear. Now, the perimeter of the walkway, remember here, if this here is going to be W plus 6, this is W, right? When I go to look at, this is going to be the width of the garden plus 6 plus, I got to add 4 here, and I got to add 4 here, which gives me W plus 14, which makes this W plus 14. This here is going to be W plus 8. This here would be W plus 8. So right away when I add the W's up, I know I'm going to get 4W, but 14 plus 14 is 28, plus 8 is 36, plus 8 is 44. So this is the perimeter of the garden. This is the perimeter of the walkway. And when we talk about both of these, they are linear. What is the relationship between the width of the garden and the area of the walkway? Well, what is the width of the garden? Well, right, the width of the garden, we said is W, okay? Now, the area of the walkway. This is the tough one, right? What I have to do is, if this represents the walkway, right? What I basically have to do is find the area of the entire rectangle. So remember, to find the area, what I'm going to do is take the W plus 8 and multiply it by the W plus 14. That would give me the area of the whole figure. So W plus 8 times W plus 14, this is the area of the whole thing. Now what we're going to do is we're going to subtract, right, the area of the garden. And the area of the garden is just going to be the W plus 6 times, what is that other side? Just W, right? So you have your width times your width plus 6. So now when I look at it, no matter what, when I go ahead and multiply this all out, what I end up getting here is a quadratic function. Because I would get W times W is W squared, and it would end up being quadratic. Okay? I'm not going to lie, not a big fan of a lot of wording in that problem. So here, if I have 1/3 to the x minus 2, this is a function. It's going to be exponential, right? Meaning it's going to grow at an exponential rate. And D, if I was to graph this, right, or create a table, and that's all I'm going to tell you to do in the calculator is graph it and make a table. The next one, if I was to look at this, if I were to connect these dots, they would be in the shape of a parabola, which means it's a function. This is going to be quadratic, which means it has a linear rate of change. And if I wanted to make a representation, I can create a table, right? And anytime I can, I'll put the vertex in the middle. Okay, because I want to show this symmetry, but I could also look at this one. It's actually an easy explicit to write, because right away when I look at it, f of x is just equal to x squared. And you'll learn later on that this is what we call the parent function for a quadratic. All right, so I know this is a lengthy assignment, but let me know if you have any questions.